The Earth is in constant motion, and we move along with it. However, what if it were to suddenly cease its rotation? Well, one consequence would be an increase in your weight, but that would be the least of our concerns. The Earth's rotation plays a crucial role, essentially governing the passage of time in our lives. At the equator, both the Earth's surface and everything on it spin at a speed of 465 meters per second. As we get closer to the poles, the need for such rapid movement to maintain the Earth's daily rotation diminishes. All of us are part of this rotational motion of the Earth. If we were to apply an abrupt brake to this celestial spin we once called Earth, the results would be catastrophic. Instantly, everything not firmly situated at the poles would continue to move at the same velocity and be swept eastward at an astonishing speed of over 1,600 kilometers per hour. You wouldn't be propelled into outer space because the escape velocity for that is 11 kilometers per second. However, your body would instantaneously transform into a 9mm bullet, or more precisely, a supersonic tumbleweed. Due to the atmosphere's gradual slowdown, individuals aboard airplanes, provided they can navigate through the ensuing turbulence, stand a better chance of survival. Astronauts residing on the International Space Station will find themselves in an even more advantageous position. However, it's improbable that anyone will be waiting for them back on Earth. The runways will unexpectedly become gateways to a colossal planetary graveyard brought about by the Earth's abrupt halt. Those very close to the poles might initially fare better, but their situation will deteriorate rapidly. Powerful wind gusts, akin to those seen following a nuclear bomb detonation, will sweep across the Earth's surface and ascend into the atmosphere, generating unprecedented global storms. The continuous collision between the Earth and these winds will produce enough friction to ignite massive fires, causing unparalleled erosion and the destruction of anything remaining in place after the cessation of rotation. The sun will appear frozen in the sky, and a single day will extend to a full 365 days instead of the usual 24 hours. Without the Earth's rotation, the protective magnetic field that shields us will vanish, exposing us to a deadly influx of ionizing radiation from the sun. The oceans would surge onto the land in the form of tsunamis reaching heights of approximately 1 kilometer, inundating nearly all continents. Subsequently, the water would redistribute toward the poles due to the stronger gravitational pull in those regions. The basins, no longer constrained by the rotational force, would be unable to retain their contents. However, as the Earth sheds the excess 42 kilometers it gained around the equator due to rotation, gradually transitioning into a more spherical shape, it might allow the oceans to at least partially return to their previous positions. This is what would hypothetically occur if such an event were to take place. However, in reality, this scenario is extremely unlikely. But let's pause for a moment and explore why, despite the Earth's rapid rotation, we do not perceive it, nor do we experience vertigo. Fortunately, the reason lies in the smoothness of the change in speed, primarily due to the immense size of our planet. It's akin to driving a car through a left turn that spans 9,500 kilometers over the course of 6 hours. The turn is not sharp enough to elicit a noticeable response from our senses. Nonetheless, this change in speed is genuine, and it results in a reduction in our weight due to inertia. On our rotating planet, our velocity is in a constant state of change, but it always remains tangential to the circular path we traverse. Inertia is a fundamental property inherent to matter, which includes your own body. In the absence of external forces, we would gradually move away from the Earth's surface. Fortunately, gravity exerts a centripetal force on us, directed towards the Earth's center. This centripetal force is essential to keep us on a circular path, and it subtracts from the total gravitational force exerted by the Earth on our bodies. The remaining force is what gives us our weight, pushing us towards the Earth's center. If the Earth were to suddenly stop its rotation, particularly at the equator, the absence of the centripetal force would cause you to weigh approximately 0.3% more than your current weight. Conversely, If the Earth were spinning 17 times faster than its present rate, the gravitational pull would be entirely offset by the centripetal force opposing inertia, rendering you weightless. So here's an idea for your diet. Just hope the Earth starts spinning faster and enjoy the seconds of life without self-injury. Interestingly, we have precise knowledge of the duration of a second. It is defined by the behavior of the outermost electron in the cesium-133 atom, which resides in a state of rest. Only the nucleus of the atom interacts with this electron, causing it to transition between its two energy levels with remarkable consistency and speed. Consequently, after precisely 9,192,631,770 of these vibrations or transitions, 1 second elapses. Exactly 1 second. This definition provides an unparalleled level of accuracy and consistency in time measurement. Atomic clocks, which rely on this principle, are the most precise measuring instruments ever devised by humans for this purpose. The reason we can't define a second solely in terms of Earth's rotation, such as a fraction of a day, is due to the variability in Earth's rotation. Small changes in the distribution of mass on Earth, caused by phenomena like earthquakes, melting ice, or even human activities, can affect the rotation rate. Additionally, gravitational interactions with the Moon, which create tides opposing Earth's rotation, contribute to variations in the rate of rotation, generally causing it to slow down over time. These changes are exceedingly subtle. They accumulate over millions of years. In approximately 140 million years, a day on Earth is projected to last 25 hours instead of the current 24. While this may not seem dramatic, it has practical implications, particularly for precise tasks like data transmission with GPS systems, where accuracy is paramount. So as a solution, scientists are measuring the length of a second using atomic clocks. International Atomic Time. Scientists monitor the Earth's rotation by periodically observing stars and quasars to track changes in the planet's rotational speed. The results of these observations determine whether adjustments, such as adding or subtracting a second from the current year, are needed to maintain coordinated universal time, commonly used in devices such as cell phones. Since its inception in 1972, this time has undergone 25-second adjustments to reflect the constant need to update it due to discovered inaccuracies. Thus, present and future time is only an approximation. This may seem unusual, but as Dimitrios Martashis said, we save lives and shorten them. We add time and we can take it away. And in both cases, we do so with absolutely no understanding of what life is and what time is. Nevertheless, we appreciate your time with us and thank you for watching.